Now let's take a look at the power and intensity of sound situation. As pressure wave travels, well, if you still remember the first picture, that is along, for example, on a thin, long tube, we have fluid inside, and a compressional pulse travel from left to the right, as we call pressure wave travels. Each element of fluid exerts a force on the element ahead. Obviously, the one behind has to push the one in front of it. So therefore, there is a net force on any slice of element that we pay attention to, that is cross-section area times the pressure difference, because this is called pressure wave. Now we already know that the delta P has an expression of delta PM max and sine kx minus omega t, that we just reached that conclusion. So if there's a net force, then we learned that before, power is associated with the speed and time the force. Now in this case, the speed you define as a partial f and a partial s and partial of t, because that is the change of displacement of the element over time, that is the speed of element move. That is different compared to the speed of sound move. Okay, so physically this element has a displacement of partial s over partial t. This is how fast the element move. How fast the element move times the net force on it. That is the power, as a matter of fact, delivered to this element. If we replace the net force F, and also we come out this partial S, partial T, was, you remember, S displacement of the function of x and t. Originally, we have that equals to Sm of cosine kx minus omega t. So if we do partial s, partial t, we assume that x is a constant. We have negative, then this omega, negative comes from cosine change to sine. But when we partial t, there's another negative comes out, which is negative omega, and this Sm remains, cosine change to sine of kx minus omega t. So we have a result of partial s, partial t as omega Sm from here of sine kx minus omega t times the net force F. The net force F, on the other hand, has such expression. So if we combine these two, what we can have is that pressure, I should say power, being delivered to that slice of moving fluid element equals to, this A is cross-section area, omega is the angular frequency associated with the wave, delta PM is the pressure amplitude, and we have displacement max Sm, and sine kx minus omega t is squared. So if we know that delta PM has something to do with K and density of fluid, speed of sound, and max Fm, we can plug in this to replace that delta PM. What we have is power equals to A delta PM square rho V, that's sine kx minus omega t and square. Now, this is the instantaneous power delivered to a position of x at time t moment to that slice of moving fluid. If we want to know average, the average of sine square is 1/2. Therefore, the average power comes out as A of delta PM square, and this is the factor of 1/2 and rho v. Let's take a look at this result. The average power is proportional to the delta PM square. On the other hand, that delta PM is proportional to the SM. Therefore, our conclusion is that the average power depends on the displacement of square. So we say that is proportional to the amplitude of the sound wave square. Well, power is in watts. And a more precise definition, we should care about how much power being delivered to a unit area. For example, if we have a source of power of 300 watts, and then when a wave spread, this is the so-called wave front, three-dimensional. So the surface is a spherical surface, which is 4 pi of r squared. R is the radius of this sphere. Now, if this 300 watts is evenly distributed on the surface of this sphere, and then the larger the sphere is, the less the per unit area the power will get shared. So it is very important to define per unit area how much power is on it. This is what's so-called intensity. We define intensity I equals to the average power, so-called averages, that we want to eliminate the time fluctuation and just taking about the average. So intensity is the average power divided by the total area. So if we consider a point source and a spherical wavefront, then that equals to the average power divided by, because the wavefront always has the shape of spherical, so that's 4 pi of r squared. This tells us that the intensity of sound is inversely proportionally to the distance squared. Now, intensity looks like equals to, has a unit of watt per meter squared. And we're not used to that because we cannot associate very much with the loudness, because intensity, in other words, is the loudness of sound. It is more convenient we define a logarithmic scale of intensity we call sound level. SL stands for sound level. Sound level mathematically defined as a number 10 times 10 log base is a log of intensity of the sound at that location divided by a reference intensity. The reference intensity I naught is chosen a number 10 to negative 12 watt per meter square. That is because this is the threshold of human hearing, which means if on our eardrum, if we can receive such a intensity, which is 10 to negative 12 watt per meter square, that we will be able to hear. That's defined as the faintest sound. So the ratio of any intensity over that reference intensity will give us an idea how loud the sound is. For example, that we say the threshold of pain for the ear is when the intensity of 1 watt per meter squared. This is obviously tested by the lab. So when that happens, we plug in this 1 watt per meter square right over here. The result we will get is, for the sound level, is 120 decibel. And I'm going to show you how we get that. Okay, sound level equals to 10 of log. Now, if the intensity is 1 watt per meter square, and I naught is 10 to the negative of 12, same units. So units cancels. This gives us of 10 log of 10 to the positive 12. This is obviously 120. Now the unit that we decide to give to the sound level is called decibels of dB. So the laboratory showed us when the intensity of sound registered by the eardrum is around 1 watt per meter square, that we feel pain, which means we cannot sustain more than that. That's called the threshold of pain. According to this mathematical formula, it comes out as 100 decibel. Therefore, this tells us if the sound level if it's louder than 120 decibel, that will cause obviously a lot of pain and also cause damage to the nerve of our ear. There is an interesting table on page 520. That is table 17.2. It said the sound levels, source of sound listed, say nearby jet airplane or a siren or subway. For example, near a jet airplane is 150 decibel. That is way too loud. And a machine gun is 130 decibel. And a rock concert is 120 decibel. And subway is 100 decibel. Busy traffic is 80 decibel. But it is very interesting that mosquito buzzing we consider is very faint, but it still has 40 decibel. So this is because the definition of this logarithmic scale, it is not linear. Now let's take a look at example problem. Say we have a source of power 300 watts. We want to know if we stay that close to a, say, speaker of 300 watts, if it's 1 meter away, what will be the sound level? How do we do the calculation? Now we start with definition of sound level equals to 10 log of intensity divided by the reference intensity. So this tells us we need to find the intensity of this source, which is average is 300 watts, and this is a point source, so we divided by its spherical surface with 4 pi r squared. Now obviously how big is the area of the sphere depends on how close you are to the source, and right now we define distance is 1 meter, so r is 1 meter. So we have this 300 watt is SI unit, and 4 times 3.14, and r is 1 meter and square. So this gives us a result of 23.9. And obviously this is about intensity, so therefore should carry unit of watt per meter square. Now once we obtain the intensity, we can easily calculate the sound level. That is sound level in this case, that is 10 of log, and we have this 23.9 as the intensity divided by the reference intensity 10 to the negative 12. Now what do we do? What we should do is write this as 2.39 times 10 to the, this negative 12 to the numerator is positive 12, and then it's 13 because 23.9 now we change to 2.39. Log A times B is log A plus B. So we have 10 of log 2.39 plus log of 10 to the 13. Log 10 to the 13 is 13. And log 2.39 comes out as 0.378. And this is 13. So obviously if we follow the strictly follow the significant figure, that doesn't make sense because this is a integer without decimal and this is all just behind decimal. So I say let's pick this as 0.4. So 13.4 times 10, that is 134 decibel. That is very loud. As we remember, 120 decibel is the pain of the threshold. So therefore this is very loud. We do not want to stand 1 meter away from a 300 watt point source. Now how about 10 meters away? Do you think it will reduce to 13.4 decibel? No, I don't think so because this is not linear. So let's take a look. How do we do calculation? There's actually easier way to do it. For example, all the difference is the intensity part, right? So say for example, we know when R is 10 meters away, the intensity level is lower. So let's name this is SL1, and what we want now is SL of 2 when R equal to 10 meters. So we better use SL1 subtract SL2 because when you are closer, sound level is higher. So that will give us a positive number. Now, if we look at the equation that we use that SL1 minus SL2, actually that result is 10 of log of 1 minus 2. A log A minus log B, as a matter of fact, that's log A divided by log B. So we have this log of that is A divided by this is B. That is times the reciprocal of that. So that is this one times the reciprocal, the other one. That is this. The constant I0 cancels. The ratio of I1 over I2. Let's look at intensity case. The intensity defined as power divided by 4 pi r squared for point source. Now we talk about same power source. Okay. Therefore, the ratio of the intensity actually is the reciprocal ratio of r squared. So the result is 10 log I1 divided by I2. It should come as R2 over R1 that gets squared. Since this is the case that R2 is 10 meters and R1 is 1, so the ratio R2 over R1 is 10. So this ratio is 10 gets squared. But we don't have to write that way. We have 10 log 10 to the 2 log 10 to the 2. So that comes as 20. What does that mean? The sound level is 20 decibels difference. So 1 meters away, that is 134 decibel. 10 meters away, that is 1 of 14 decibel. Isn't that very interesting?